So thank you for being with us today. I'm happy to see all of you here for this talk, which is part of the CIS colloquia. As you know, with these seminars, you provide a platform that brings together professors and researchers from EPFL and researchers and thought leaders from around the world working on different aspects of intelligent systems. Last month, we had the pleasure of hosting Professor Michael Brunstein for a talk about his work on geometric deep learning. Today, we are delighted to have Professor Vijay Kumar with us. Vijay is the Dean of Penn Engineering at University of Pennsylvania. To give you an idea of what to expect, the talk will last for approximately 1 hour, with Professor Kumar presenting for 45 to 50 minutes. The talk will then be followed by a Q&A discussion that will be moderated by Professor Auke Isbert, the head of the Biorobotics Laboratory and member of the CIS Scientific Committee here at EPFL. So please, if you have any questions during the talk, feel free to submit them directly via the chat, and we'll take them up later on during the Q&A session. So before diving into the presentation, I would like to thank Professor Kumar for his availability and the entire team for organizing this event today. Please join me now and welcome Professor Auke Isbert for the words of welcome for our speaker.
Yes, thanks a lot, Jan. So welcome, everyone. It's a really great pleasure to welcome you today, and especially big thanks to Vijay Kumar, who is a very well-known roboticist. So we're lucky to have you, Vijay. Thanks a lot for being here today, because you're a person who has been very influential in terms of collective robotics, both ground platforms with flying platforms. And I think you're a perfect example of as a developer of intelligent systems, which is our center here. So we are very happy to have you here. I think everybody has read your bio. You're very well known, but I want to highlight that you're an IEEE fellow. You have received many awards. Also, you're a member of the National Academy of Engineering. And now you're the Dean of the School of Engineering at UPenn. So thanks so much for taking the time to be with us. And I'm very much looking forward to your talk.
Thank you very much, Auke. Thank you, Jan. Thanks to all of you for hosting me. I wish I could be there in person. Lausanne is a beautiful city, and I have fond memories of visiting before. Also collaborations with colleagues, Alcario Martinoli, his group, we've written papers together. His former PhD student did a postdoc with me, Amanda Prorok, who's now at Cambridge. And a former PhD student of ours, Salman Sakar, who's a professor and the director of the microbiorobotics lab. So a lot of strong connections to EPFL, and it's a shame that we're doing this virtually, but alas, that's the world we live in. I want to spend a few minutes, as Auke said, talking about my work on swarms of robots, particularly flying robots, and maybe tell you a little bit about our thinking on this topic and how things have evolved over the last 10 years and some of the challenges we're trying to address. So I want to start by talking about robot swarms in general, how at least those of us who work on collective behaviors think about robot swarms, and then talk about specifically swarms of micro-aerial vehicles, and then go into some of the challenges. I'll talk about 5 different topics at a very high level, and then get into some applications. So if you were to develop a taxonomy of collective behaviors, in my opinion, you want to think about 4 things. First is scale, that is the total number. You could also think about time scale and spatial scale, but I'm thinking in terms of total numbers. And then the types of tasks that collective behaviors might be used to accomplish, the complexity of the environment, and then finally, this question of heterogeneity, where you might have different types of robots collaborating with each other. You could also do the same thing in nature. This is a chart that David Skelly from Yale University and I worked on, cataloging different types of group behavior seen in nature. So here you'll see that larger group sizes are found in smaller animals. And the red and the blue lines indicate evidence of centralized behavior, where you see red, and blue are, the lower level organisms, larger groups, where things are definitely decentralized. So for example, if you look at lions and whales, they tend to be leaders and things tend to be more tightly controlled. So what I'd like to do is further break this up. We think about small groups And so from a computational perspective, if you think about numbers from 1 through 5, you can actually reason about the combinatorics, maybe even 1 through 10. And beyond that, it becomes really hard. But in small groups, individuals can be labeled. They can learn to identify their neighbors. And things are a little different when you get to larger groups. And I'm going to call them flocks. And where I think of group sizes from 10 to 100, where the combinatorics become very hard. And yet you want to retain some sense of the identity, as opposed to swarms, where you can have abstractions, where you ignore the details of the individual, you can ignore the labels, and you can assume that the agents are altruistic, they're replaceable, maybe even anonymous, and the communication is completely indirect. So in some sense, the hard problems are in the middle. In the smaller end of the group size, you can actually brute force the combinatorics. You can come up with calculations. Even if it's NP hard, you can kind of do it by force. All the way on the right side, when you see the swarms, you can develop abstractions, and abstractions that allow you to model the group without worrying about the details of the individuals. But in the middle, the numbers are large, and you cannot ignore the individuals. And that's where some of the challenges arrive. Going back to swarms, the easiest way to build a swarm, as Professor Sakar now taught us, is to think about this context in bacterial swarms. So these are experiments conducted by Salmon. The easiest way to build a swarm, you build a cell culture on a petri dish on an agar base, and these happen to be Serratia marcescens, and you'll see the swarming behavior develop naturally as the bacterial culture grows. And so the individuals swim between 30 to 45 microns per second, but they interact with each other, and pretty soon you get these patterns. On the bottom left, you essentially see a picture of a microstructure, 100 micron by 10 micron by 10 micron microstructure with these bacteria blotted on them. So if you take the structure and you blot this culture, you will essentially have these bacteria sticking to the microstructure. And on the right side, you'll see a video. You let the bacteria now swim, and now they're carrying this microstructure, if you will. And you essentially see a swarm doing something useful, which is carrying a barge across a fluid channel. And then you can play other games, as Salman taught us. You can impregnate the SU8 with iron oxide particles, and then you can think about controlling something which is composed of the bacterial swarm, as well as something that you might be able to control using gradients of illumination or chemical gradients. And you see robot-like behavior, but essentially being enabled by hundreds of bacteria or even thousands of bacteria, and very much in the spirit of swarms. So these are some examples of swarm behavior. I want to talk a little bit about the kinds of tasks we might think about, which is sort of the second way to characterize collective behaviors. So I want to start with the simplest type of task, and this is captured by the word coordination. So coordination refers to multiple agents acting in concert, acting in harmony, much like we saw with bacteria. So this is the simplest form of collective behavior. On the other hand, we can think about deliberate acts where agents come together to cooperate to perform a task deliberatively, as opposed to the first example, coordination, where things are a little more emergent, a little more natural. And then finally, even more deliberative is this act of collaboration, which requires heterogeneous agents, agents of species A and agents of species B coming together to do something that neither one could do themselves. And as you get from coordination to cooperation to collaboration, things get more complicated. And of course, there are other C words to complete the alliteration. You can think about competition, coalition formation, cohesion of groups. But the important other C word that I want to use is communication. So as you go from coordination to cooperation to collaboration, communication becomes a lot more important. And I want to say a little bit more about that, a problem that we don't fully know how to incorporate into swarm behaviors. So let me say a little bit about these different tasks. So coordination, I think of as something where the cost function is well defined. You want to accomplish a mission. Agents have the same cost roughly, and the cost function is just obtained by adding up what individual agents do. It doesn't matter which agents are involved as anonymity, and you think about coverage, you think about search, you think about flocking, you think about rendezvousing. All of these are examples where individuals are not particularly important. It's the group that's important. More the numbers you have, such as in coverage, the efficacy improves linearly. Well, up to a point. After that, coordination doesn't work. But essentially, you want to cover an area. If you have n agents, you'll do it n times faster than a single agent. Cooperation is a little more complicated, where individuals might have different types of goals, different types of tasks in mind, but they come together to perform a common task. And oftentimes the efficacy is a nonlinear function of the number. So here's a very simple example, some work that Spring Berman and colleagues did, along with a collaborator from Arizona State, Stephen Pratt, studying desert ants. So what you see is these ants cooperating to carry a morsel of food back to their nest, happens to be a piece of fig. Here, the number is small. Technically, you can reason about the combinatorics, but these ants are able to recruit their neighbors because individually they cannot do this task on their own. So if you plot the success of this task as a function of n, you will see there's a critical number beyond when suddenly the performance ramps up. So there's an inflection point. So this is an example of cooperation. Again, homogeneous agents performing a task, modest numbers, not swarms, not coordination, but where you really need to think about individuals' roles in these tasks. And then finally, something we're working on, which I don't have the time to talk about, is more collaborative behavior. We all know about these airplanes that have disappeared underwater. Think about the problem of finding a big jetliner in the Indian Ocean. This is not a simple task. And you might think about using underwater robots to find this airplane. You might think about surface robots, autonomous surface vehicles, small vehicles, large vehicles. You might think about aerial vehicles providing support for search. Perhaps vehicles that are flying low to the ground. You might have communication links that are not that are sporadic, that can easily get broken, sometimes short range, sometimes long range. You want to detect, classify, localize targets. This is a complex problem where none of the paradigms that I spoke about earlier can be easily used. You really need to think about different types of agents, their different capabilities, and this is where collaboration comes in. So just an overview of the field. Let me continue the overview by telling you a little bit about swarms of microaerial vehicles. And so I want to tell you, first of all, I mean, there's a lot of cool work being done at EPFL, certainly with Professor Dario Floriano's group and others. I'm going to talk about something where the mechanical innovation is not that great. Maybe it was great 10, 12 years ago when we were first working in this area, but now this is all commoditized, off the shelf. I want to start with to my knowledge, the first known demonstration of swarms. This happened in our lab back in December of 2011, where we were able to use 20 microaerial vehicles, admittedly in an indoor environment with a motion capture system, where individual vehicles knew exactly where they were in the environment and relative to their neighbors. And here you see a number of very simple tasks where they're able to change the formation to accommodate obstacles, again, in an environment that is completely known, completely characterized. The big challenge here is to control 20 vehicles with simple group abstractions that an individual could program in without worrying about the combinatorics of the 20 vehicles. Now, this is all commoditized, and I just chose two very US-centric pictures to demonstrate this. Those of you who follow sports may not be aware that American football is not football. It's a very different game. But our local team is the Philadelphia Eagles. So a company, Verge, which is right next to my lab, which started right next to my lab in an innovation zone, they basically took this technology, and you can see an eagle, the Philadelphia Eagle, being shown off early 2020. And the Biden victory celebration, this happened very near where I live. You can see drones forming the letters Biden. All of this is now commoditized. There are companies now that do this, and it's become relatively simple to do as long as you have really good GPS. But in all of these, and by the way, there are other examples of this too. Most recently, one in Hong Kong used by a company to demonstrate a luxury car. But why is this commoditized? Well, if you know where the robots are, you can choreograph these patterns, and it's easy to automate the process. And just to give you an idea of how you might automate this, let me just tell you about this cartoon problem where you have drones at S1, S2, S3, the start locations, and you want them to go to a goal location, but you're not going to tell them up front which goal location to go to. And imagine that the red goal locations are part of a pattern. So you might think about essentially first labeling the destinations, and the first challenges, finding the right goals, right labels, assigning the robots to goals. And this is obviously a goal assignment problem. And the second problem is planning trajectories. And here you have to plan safe trajectories that respect dynamics. And then you want to do this with safety considerations. So imagine you have robots whose shape, maybe they're circular robots. You want to make sure that these robots don't come within 2 times the radius of each other. And then finally, ideally, you want some optimality. You want some smoothness. And so we tend to think about the fourth derivative of position and try to find the best possible trajectory that minimizes this fourth derivative of position over time. It's called the snap. And the two challenges here are first, assigning robots to goals, which is a combinatorial problem. The second is a continuous optimization problem, the planning of trajectories. And you want to do this concurrently. You want to concurrently assign and plan trajectories. So some work done by my former PhD student, Matt Turpin, he showed that if you concurrently solve both these hard problems, it's actually doable if the robots are interchangeable. In other words, there are no labels attached to robots. Any robot can be used to fulfill any goal position. And there's a whole host of literature going back to the assignment problem by Harold Kuhn and James Moncrief. This is a 1955 paper, a classic. This is still used in the Operation OR research community. But Matt's work essentially looked at the problem with obstacles in the sense of robots avoiding each other. And he solved this capped problem in a centralized way, both in R2 and R3. And an extension to that, in a decentralized setting, the centralized one has guarantees. The decentralized one does not have a liveness guarantee. It has safety guarantees, but it's not live. And then finally, a spherical robot with obstacles in a very, very cluttered environment. So these algorithms are now been commoditized over the last 6 or 7 years. So to have swarms in a completely structured environment where I know where everything is actually not that hard. If you look at swarms of microaerial vehicles, this is a picture that I adapted from a paper was referenced below. The circles indicate centralized infrastructure, either GPS or motion capture. The red labels refer to our own work. And the X's refer to fully autonomous, no infrastructure, no onboard sensing, GPS denied. And some of the early work was done at Penn, at ETH, and at CMU and MIT, where essentially a combination of LiDARs and cameras and IMU was used to localize and then navigate the robots. But coming back to swarms, a lot of impressive demonstrations, as you can see on by the blue circles on the top. And at USC, one of my former students, Nora Ainian, probably did the best non-choreographed swarm work where she showed a 50 robot swarm, which could essentially be used to navigate to patterns that were specified up front. Coming back to commercial efforts, I think some of the most capable companies are DJI, of course, the big drone manufacturer in Hong Kong and China, and Exyn Technologies, a spin-off company from our lab, and then Skydio, a spin-off from MIT. I want to show you, however, a similar attempt, and I'm going to try to turn down this video. Sorry about this volume. You'll see something similar, but now without GPS or mocap. This is work that relies on the Snapdragon chipset developed by Qualcomm, a collaboration with Qualcomm, where essentially we're used to use the bare bones, the guts of a smartphone to essentially do visual odometry and integrate that visual odometry to get trajectories, and then feedback control based on trajectories that are pre-planned. All the compute, all the sensing is running on board. There's no GPS, no motion capture camera system. And again, in this case, Aaron Weinstein, former student, and now Giuseppe Loiano, who's a professor at NYU, they essentially can control the swarm by simply specifying the pattern and specifying where the pattern needs to go to. The robots decide which robot needs to go to what location and how and when, in order to form the pattern in a safe way. So this was probably the first of the set of swarms without any external infrastructure. And again, I'm going to go back to my chart to show that, yes, we did this back in 2018, 2017, 2018, but there are a lot more groups now, groups like at Delft and Hungary that have actually gone further ahead in terms of the number of microaerial vehicles. This is going really well, except there's some degree of centralization. Almost all these efforts, I think all these efforts require some kind of a base station with ad hoc, with a with some communication network and some centralized computation. So the main question we are trying now to address is, how do we do all of this in the wild? The key challenge is to essentially have better perception action loops. Robots must be able to see and identify their neighbors and then take actions based on what they see. This is not an old idea in robotics. Certainly, observations inform actions, and then the reverse is also true. If I want better perception, I can move to get better observations. But what is new is the challenge of synthesizing perception action communication loops, where we think about communication in the same way we think about perception. We want to communicate to make better observations so that 2 agents, maybe 3 agents, can get better observation than a single agent. Likewise, the perception can be shared. The observations can be shared to get better estimates. Communication loops can inform actions. And then if you cannot communicate with an agent, you can actually move to communicate with the agent. So one question is, how can we design perception action communication loops to enable more capable swarms? And the first thing you realize that you need an autonomy stack that works on a lightweight platform. Otherwise, all of this doesn't work. You need perception action and communication working on platforms. Here's a bunch of platforms we've built over the last 10 years. And one failure with rotorcrafts is when you try to hover, and that's the best mechanism for fast maneuverability in unstructured environments, you end up consuming roughly 200 watts per kilo. I'm a mechanical engineer. I understand that this is inefficient, and we should be looking to more efficient mechanisms like the ones that people at EPFL are working on. But if you want to build swarms, this is the easiest way to build lots and lots of vehicles and get them working together. I want to highlight 3 platforms. The one on the left side is equipped with a LiDAR, a stereo, an Intel i7 CPU, and can do fast navigation, 5 to 10 meters per second in cluttered environments. The one on the right side is the lightest platform, the smallest platform, but of course it needs a motion capture camera system to operate. The one in the middle is 1.3 kilos, It is equipped with a stereo camera, a TX2 GPU, NVIDIA TX2 GPU, and an FPGA, no CPU. And this actually works with a depth camera, a 3D camera, allowing you to navigate fairly complex environments, but doesn't work in bright sunlight. So a lot of trade-offs here. And we've been trying to make these vehicles smaller and smaller. And the smallest vehicle, again, leveraging the Qualcomm Snapdragon chipset, is a 133 grams quadrotor, very impressive motors, impressive thrust to weight ratio, capable of fast maneuvering. I'll show you some results in a minute. But again, trying to get everything that we need for perception action communication loops on board. So this particular vehicle has a forward-facing stereo camera, a downward-facing wide-angle camera for visual odometry mostly, and is able to navigate at speeds of roughly 5 meters per second. So why is the autonomy stack challenging? Again, much of the success we've had is based on platforms that are equipped with cameras and IMU and with LiDARs. And the cameras and IMUs are great for state estimation, but LiDARs are essential for planning fast movements in cluttered environments. And basically what we end up doing is trying to solve the time optimal control problem or the minimum snap problem in real time through complex environments. So what makes this problem complicated? Well, the environment is not fully known up front. You only know it to a finite horizon. You're operating in extremely cluttered environments. The environment is non-convex. Actually, it's even worse because you can actually think about different trajectories and they'll lie in different homology classes. You want to reason about that. And the relative degree, it's a fourth degree system, and there are input and state constraints that make it really challenging to solve this in real time. So this is all of this we want to do on board in an ideal world. I want to show you an example of how we do this. This is an experiment where you will see 5 meters per second flight, roughly 700 meters to the target and back. The target is given to us. It's this asterisk that you see on the right side overlaid on the Google Earth image. But what the robot knows is in the bottom left. What it sees is on the top left. You'll see it building a local map. Remember, it has no GPS. It only knows that there's a target, an approximate location. It has to go find the target, come back, report back to base. The target happens to be a red barrel. And you will see this plan motions that allow it to go around the trees in real time. You'll see a lot of rolling and pitching, and that's because of the dynamics and reacting to obstacles that are just seen. It gets close to the building. It still knows that the target is somewhere close by, but it can't see the target because the target is on the other side of this wall. So it patiently skirts the building. The speed here is a little lower, maybe 3 meters per second. When it turns the corner, it'll find an opening. And you'll see it adjust from the bright illumination outdoors to the dimly lit indoors, adjusting to the contrast. Many obstacles have been placed in the way, obstacles that we're not aware of. By the way, this is part of a DARPA-sponsored project. And so they would set up this environment, and we had to go in and find the object of interest. And here you'll see the object of interest happens to be a red barrel, very easy to identify. That's not the challenge. The challenge is really going to the target, locating as quickly as possible, coming back to base and reporting where the target is. This is an obvious for search and rescue type missions where you're trying to look for objects of interest, perhaps human beings, perhaps explosives that have been placed there by bad actors. And you want to come back and say, this is where everything is. So you'll see it come back, and at every time it's capturing local images and it's building a map, but it doesn't store the map. If you really wanted the map, you'd have to reconstruct it offline. The goal here is to go as quickly as possible to get the object of interest. So this is the autonomy stack that we want to run on robots, and it becomes really, really hard as you scale things down because of inadequate sensing and inadequate computing. But there are some benefits of scaling down, and the main benefit is, of course, something we know from nature. So this is a swarm of honeybees, and because of the low inertia, you can see that the collisions that may occur have a very low penalty. On the bottom left, we'll try to recreate these with our 25-gram micro UAVs with planned mid-air collisions. So these videos are slowed down by a factor of 20. And you'll see perhaps the first planned mid-air collisions, and the robots recovering from that quite easily. Again, the cages are just to make sure that the propellers don't get entangled. And on the bottom, you'll see some of these experiments being conducted in obstacle-filled landscape. And planning is very different. Autonomy is very different. You don't have to worry about the exact location. You don't have to worry about the exact location of the obstacles, and you can afford to sustain collisions. So this is really where we're headed to, and our first attempt is to be able to do this without the motion capture camera system, where you'll see the tier cell platform is able to detect collisions and able to react to it, admittedly much slower. This is a speed of 1 meter per second, about half walking speed, based solely on inertial measurement units and the images that you see on the bottom right that the robots are collecting. So every time you detect a collision, you know that your visual odometry suffers a discontinuity, and you will have to learn to recognize that discontinuity and be able to develop a filter that allows you to navigate in the presence of this collision. So work by Ren-Chin Liu and Yash Mulgaonkar, who designed all these platforms. And the fourth thing we're trying to do is to develop open source experimental platforms that will facilitate collaborative autonomy. So in robotics, the availability of platforms has always driven very, very interesting research. And what you see here are a whole host of platforms enabled by the Snapdragon chipset, and also a company we collaborate with, a small startup called Model AI. And Model AI provides us an integrated hardware setup that allows you to control the motors, also get the VIO working robustly on these small scale platforms. And you can see each of these platforms is actually now available open source, both the reference hardware design and the software design. And you can also equip them with lights, and you see as on the top right, you'll see them navigating in smoke-filled environments and environments where water's dripping from the ceiling, environments that, of course, you don't know, at more modest speeds, because all the imaging is now being done by stereo cameras, and we move very, very cautiously here in these cluttered environments. So I'll show you a video of these robots. Actually, COVID was a blessing in disguise. We had to leave our labs, which meant we had to operate wherever we were. And so you'll see a lot of the students actually set up experiments in their homes, as you'll see in a minute. And here, these robots have a combination of Wi-Fi and Zigbee mesh networks with both peer-to-peer communication and communication to a server. You can see the net payload, besides the electromechanical components, is only 63 grams. We use stereo cameras facing forward, downward facing cameras for navigation, also equipped with a thermal camera or time of flight sensor. So these are now operating in Dinesh's living room. The only thing you see in terms of an external infrastructure is essentially an April tag. The main reason for the April tag is because they need to know where the origin is. So once they take off, they don't need to worry about the origin, but they do keep track of the origin anytime they fly over it. So you'll see a 3-robot team. And again, this can operate. You can take this anywhere you want. It doesn't even have to be an April tag. It could be any object that you know that is easy to identify. But those are landmarks that are kind of essential in a robot world. We don't know a priori any a reference point for an origin. Let me fast forward this. I do want to show you some operation outdoors. So this is in the laboratory. Again, we happen to have a Vicon camera system here, but it's only used for ground truth measurements. And then you'll see outdoor experiments. I'm sorry, it's not there in this video, but this is the swarm of UAVs we have built and again available on our GitHub repository. The last thing I want to talk about very briefly is how to design these perception action communication loops for multiple heterogeneous vehicles. And what we really were working towards is a comprehensive framework and algorithms for these PAC loops. And our strategy was motivated by this very, very simple task. This is an old result going back to Reynolds-Boyd algorithm, where if you want robots to flock, all you need to do is to have these robots operate based only on relative position, relative velocity. And if you sum up three terms that force the robots to stay close together, avoid collisions, and align themselves, and this is the control law that guarantees that this can happen. Not Boyd's work, this is my colleagues, some work that our group did, and then Bert Tanner working with George Pappas and Ali Jadbabai showed that if you have the right framework of right setup of initial conditions, this control law will guarantee convergence. But however, as you can see from this initial conditions, which is a fairly good set of initial conditions, the robots can quickly go astray. And that's because the basin of attraction for this controller on the bottom left is hard to characterize. You know when you've picked a set of initial conditions that satisfy the requisites for the basin of attraction, but it is very hard to determine upfront what this basin of attraction looks like. And so model-based controllers are inherently flawed in this sense. So we started thinking about how can we make this control law more bulletproof. And then we came to the realization that really perception action loops might be easy to synthesize, not easy, but have a principal model-based way to synthesize things. But it's really hard to think about who should talk to whom, who should listen to whom, and how action should be taken based on that. And this is where I've become a big believer in machine learning. So while you might not need to learn how to navigate, you do need to learn perhaps how to communicate and how to take actions based on that. And so our inspiration from this comes from CNNs, obviously, but we use instead what are called graph neural networks, which are generalizations of CNNs. Just like in CNNs, you essentially look at individual pixel values and you try to do convolutions over neighbors. Here you do the same thing. In a robot network, you naturally have a graph structure and you try to essentially take belief states in individual robots and convolve that belief state over neighboring belief states. So here's the idea. The yellow agent is at the center. It talks to its neighbors. So that's the one-hop neighbors. It builds a belief state based on what the one-hop neighbors are telling it. You can go to two-hop neighbors, three-hop neighbors, and so on. So at every step of the way, you're essentially thinking about a filter. That filter has a compact support, and you are essentially averaging over what your neighbors think. The big difference, though, is that you can think about this averaging process in terms of weights, and you don't have to a priori determine what the weights are. You can essentially train those weights. So this is the central idea. And the key theoretical insight is the GNNs are essentially permutation covariant. In other words, you don't have to worry about the labels of the neighbors around you. And they're also stable to graph perturbations. If you change the positions a little bit, the graph changes, but the essential result, the behavior that you get, does not change. And so there's a Lipschitz continuity result that you can use to characterize this. The practical implication is that maybe we can use model-based approaches to find expert solutions, but for very small teams, for very small graphs, teams where the combinatorics are manageable, maybe a handful of agents. And then you can try to imitate what we know to do with small teams, but imitate that with large graphs. So that's the central idea. So I just want to quickly demonstrate three very simple results. The flocking policy that the model-based approach did not work. The same set of initial conditions, the agents get dispersed, but if you use our learned control policy, the agents essentially stay aligned, or they get into the aligned position. All done with a fairly simple two-layer, multi-layer perceptron with 16 hidden units. It's a fairly simple approach to train this. Here's another one, a formation control policy, where this is Arbaz Khan's work, where, again, training on a small graph, the robots learn how to form a V-shaped formation. And there's a fancier video on the right side, but the essential idea is the same. So once again, the learning problem is based on expert policy that is actually not too hard to find for small teams, but generalized now to very large teams. And some really interesting work by Kate Tolstaya, who recently graduated. And by the way, all of this is in collaboration with my colleague, Alejandro Ribeiro. He's the expert on graph neural networks. And so this video shows how you can essentially solve a very complicated traveling salesman problem or like problem using graph neural networks. So in this video, the environment is known up front, and you're trying to visit all the blue blobs, all the red blobs. And so it's like a coverage problem, but you essentially want to visit all these nodes in order to get the maximum information possible. And all the robots are basing their search only on local information. There is no way you can brute force this problem, but on the other hand, you can again take solutions that you might learn for small problems and then use that to train larger algorithms. And that's what you see in Kate's work, and her PhD thesis is a great reference point for this work. So let me conclude by just saying the one thing that I haven't talked about, which is heterogeneity, although we're building heterogeneous platforms. I think this is an extremely interesting area of work. Some of the early work on in this area was done, again, at EPFL by my good friend, Alcario, and how heterogeneous agents can enable collaborative behavior. I think this is a very intriguing area for research and something we are working on. But I should just conclude by saying that the future really is exciting. As you think about where technology is going, the price to performance ratio of sensing, communication, and computation is falling and will continue to fall. And I think that means a lower barrier to entry for all of us working in this field. I think 5G represents a really, really interesting inflection point. I think this idea that I have adhered to thus far, that all the computing needs to be done at the edge in order to ensure reliability and safety, may not be the right paradigm anymore. Maybe a lot of this could be outsourced to the cloud. And maybe what we think about in terms of swarms in the wild need not be all about edge computing. Some of it could be done on a cloud, which could develop organically. The only area where I don't have great news is in the battery front. Despite what luminaries like Elon Musk tell you, the battery technology hasn't changed substantially. Yes, we know how to manufacture large-scale batteries at lower cost, but it's basically the same chemistry. So as we think about applications, I think one very interesting area is to go beyond sensing and information gathering, which is mostly what I talked about, to physical interaction, something we're very intrigued. And one of my students, Jake Weldy, presented a recent paper at ICRA that is starting to address manipulation problems. Finally, an acknowledgement to the team of just amazing students and postdocs that work with me, and also research staff, Dinesh Thakur and Alex Zhu. Thank you very much for listening. I'm happy and be delighted to take questions.
Great, fantastic talk, Vijay. So I do a big round of applause. I think people are applauding virtually. So thanks a lot, very exciting. There are already questions on the chat, and I suggest we use the raise hand feature on the reactions, that we also take live questions, and I will order them so that we take them one after each other. So let's maybe start with the people who asked some questions on the chat. There are some technical questions. Maybe rather than me reading them, I suggest people just unmute and ask them themselves. So Anton Lukachuk, you had some question about the LiDAR technology. Are you there? maybe you can just unmute. Yeah, please go ahead.
Yeah. First of all, thanks a lot for a very interesting talk. Yeah, I have a question on LiDAR. Yeah, because maybe I'm doing a bit of LiDAR stuff. I think you're using time-of-flight LiDAR, not FMCW. It would be quite bulky. So I'm interested in what should be the sampling rates. I mean, how fast should you acquire the data, and what is the resolution that you need, and also the operating range for the drones.
Yeah, it's a great question. I think the resolution may be the easy one, which it has to do with the environment you're flying in, the resolution of the obstacles. So if your obstacles are big obstacles and the environment is sparse, maybe lower resolution is okay. And a lot of the inexpensive solid state LiDAR technology would actually work in that setting. I think the harder one is the sampling rate. Because it's directly linked to two things. It's linked to how fast you're navigating, and it's directly linked to how big your platform is. So in a lot of what we do, we make the assumption that the robot can put on its brakes and slow down at the rate of gravity. In other words, minus 9.81 meters per second squared, which fundamentally limits how quickly you can come to a stop. So if you do the calculation, if you're going at 20 meters per second, you need to be able to see 40 meters per second ahead. And you need to be able to sample fast enough so you can detect that obstacles. So the range and sampling rate have directly to do with how fast you're flying and how big your robot is, how heavy your robot is. And you can do some back of the envelope calculations to try to estimate that.
Yeah, okay, thanks.
So I will switch a bit between raised hands and the chat. So maybe let's hear from Dario from the raised hand, and then we'll go back to the chat.
Yeah. Hi, Vijay. Thank you very much for the beautiful presentation.
Of course, thank you.
And, you know, in my experience, and also when I see these swarms of drones, what I notice is that the more drones you add, the slower the swarm becomes. And in our experience, this comes from a number of sources. Sometimes it's perception, communication jams and missed packets, dynamics of the drones, because sometimes you don't have sufficient dynamics for turning in the right direction. But I would like to hear from you what, in your opinion, is the reason why our artificial swarms do not scale up in speed as, for example, some of the flocks of birds do.
Hey, great question. So let me first say there are multiple reasons, as you well know, that this happens. I think, you know, solving perception on board on lightweight platforms is really hard. I didn't talk about this, but we're trying to train lightweight neural nets to essentially do the detection and classification of neighbors. And this is an extremely hard problem. You know, cameras, you're trying to look at a drone that might be far away. It subtends a very, very small set of pixels, very hard to recognize based on with computational resources that are inadequate. On the other hand, if you're really close, you can recognize it, but then that might be too dangerous, right? So perception is a challenge. I think dynamics is a challenge, but we kind of know how to handle that. I think for some of the more exotic vehicles that you're developing, that might be a little bit of more of a challenge, because you have to invert the dynamics and think about the mechanics, the fluid mechanics, and so on. That might be harder. But I think for rotorcrafts, I think we know how to do that. But the third thing that you brought up is communications, and that's the part that I find the hardest. So if I were to ask you or anybody this very simple question, how far out do you need to communicate in order to get the swarm to navigate more aggressively? Everybody has this intuition, well, if I can navigate all the way to the end, I'll be somehow better. But that's not necessarily true, because as you try to communicate all the way to the end, the information gets less precise, more chances of it being dropped. And how can you model that up front? And that's why what we're trying to do is to try to learn this. So learning who to talk to and who to communicate with and how much to weight that information is something that's task dependent, environment dependent, and perhaps learned on the fly, which is a lot easier than trying to learn how to fly. If you don't learn how to fly, there's no way you can tackle this more complicated problem. And so that's why when we come to perception action communication loops, you know, we think that a good way to address this is really by thinking about looking at the specific environment, drawing data from it, and then learning from that.
Yep. Thank you.
Yeah. I like that question, by the way, because you could almost see the swarm like a fluid where obstacle avoidance and everything at viscosity. So I guess that's also the reason why as soon as you put more things, you get a bit more viscous, isn't it? Or I don't know if it makes sense. Yeah.
I actually, you may use that as an analogy, but we actually try. There's a couple of papers we've written that uses the hydrodynamics of fluids as a model for this. So you can imagine your just like in particle filters, you have particles that approximate a distribution. Here, the robots approximate the distribution of the fluid and then flow around obstacles. But you're absolutely right. I think just like in a fluid, it's really hard for a fluid to make a right angle turn. It's hard for the swarm to make a right angle turn. And so there's a lot of interesting literature on how the complexity of the graph can affect the dynamics of the swarm in a discrete setting. But you're absolutely right. In nature, you see this in a continuum setting, which plays out really, really nicely.
Yeah, thanks a lot. Yeah. Let's go back to the chat, and then I'll carry you. I saw your hand. So Jordan, are you there?
Yeah, I'm here. Thanks a lot for the amazing presentation. I'm really happy actually to see graph neural networks. We are as well interested in our group recently by them, but mostly as you discussed, as Auke discussed, in relation to fluid dynamics. And actually, we're trying to think more on how to embed physical laws as priors within the graph structures, and not only learn from let's say synthetic simulation the communication between the nodes. So this is something which is interesting. But back to my technical question, another project that we are working on is linked to SPAT. It's time of flight flash lidars, more on the side of mapping rather than navigation. But seeing that you're using time of flight sensors asks inside of me the curiosity of how do you fuse your RGB and time of flight camera? Do you use neural networks for that? So this is my first question, a bit more technical, linked to the fusion of the two different type of perception. And second is, I guess you don't do any absolute navigation. This is another topic of interest of our lab, which is more about absolute position in outdoor large-scale environment. I guess you're only focused on mostly close-range indoor relative navigation.
So that's a lot to let me try to unpack this. So firstly, Jordan, I'm very interested in the first comment you made about embodying or incorporating physics into the individual nodes as you think about fluids. So I didn't talk too much about this, but one of the things that Kate Tolstoy was able to do in this flocking problem is essentially figure out the right feature vector. And the right feature vector is informed by the dynamics, informed by the repulsion rules and the attraction rules. And they end up being nonlinear features. Of course, you can aggregate them in a linear way, but I think the physics, incorporating physics into graph neural networks really allows you to do a lot of complicated things. The second question you asked was about the real-time depth estimation and how we fuse this with RGBD images. I'm happy to send you a paper. Actually, I would love to get you a copy of your fluids paper as well, and maybe we can exchange emails, and I can share this paper with you. I'm blanked out on the third question you asked. Sorry.
Sorry, it was too much information.
Yeah. So we do absolute navigation. The reason I didn't bring this up is because I'm not so sure that to do swarms, that absolute navigation is a bottleneck. So for example, we have robots that are navigating forests, doing forest inventory. We have robots that are navigating orchards, doing fruit inventory. There you need to know where every fruit is. You want to map that, and you want to keep track of that with reference to a global reference frame. The maps we build for fast navigation, and again, I would argue that a lot of what you see in nature, they don't think about a global reference frame. So that's why I skirted that for this particular talk.
Thanks a lot,
yeah.
Vijay.
Great. So let's then maybe hear from Alcario.
Thank you very much, okay, and thank you, Vijay. It's always a pleasure to listen to you. I got one message that in your talk that I personally feel very much the same, and I don't have an answer. Is this kind of closed loop between perception, action, and communication? I think this is an absolutely key challenge that sooner or later we have to solve in order to really kind of maneuver swarms in a more agile way or more performant way and so on. But now the question is that I understood that you want to learn also the graph of who to talk with and so on. But that will imply first maybe actually understanding the environment, the mission, and I am more interested in online learning as opposed to kind of extracting things. And second, if you want to online learning, there are delays. There are actually all sort of things that it has to happen in real time, and then at the same time you have to learn. And that is to me a key challenge that I think we have to face if we care about online learning and communication. I mean, it means essentially that the swarm is learning, not just a single individual, and they share information through whatever graph and through whatever communication channel that could be explicit or could be implicit. I just kind of, you learn from the behavior of the guys without communicating explicitly. Can you comment a little bit on that?
I think this is a great question. We should have a longer discussion on this, but the way I'm thinking about it is that there are three levels, right? So one is you learn from what you know from model-based approaches to get started, right? I think that's important. Second, you train offline to do better,
okay,
right? Better than model-based approaches, but on with the knowledge that you have from physics, from control theory, from whatever else, from computer vision, et cetera. And then the third step is the online piece, which again, we don't have great results on this, but we're looking at how reinforcement learning can be used to do this. So we have some results, for example, on goal allocation, task allocation problems. But that has to be done in an online setting. I think Dario asked this very important question. I mean, the hard thing about communications, as you well know, Alcario, is all the dropouts that happen. That depends so much on the environment. So if you can't adapt to that, anything you've learned up front is not going to work. So I do think that plays an important role. The question you asked about learning at the individual level versus learning at the swarm level, I don't know how to quite address that, because I think the swarm is a collection of the individuals. And if individuals learn, it may be that they all learn the same thing, which would be the case if the swarm is homogeneous in the sense of the task. But if they're not, then so for example, this is observed in flocking of fish. The fish on the outside are the ones that tend to be hungrier. They're more aggressive. They're looking for food. The fish that are satiated, that have fed, they're on the inside. They have no incentive to do anything different. So already you see this distribution of behaviors, if you will, that the swarm has learned, but actually individuals have learned different things.
Yeah, and
so,
these generate all sort of credit assignment problems, which are not easy to solve, right?
They're not. But I think if you have some idea of what the task is, and if you have a performance function that can be locally estimated, then an RL type architecture could be learned to continuously adapt to this.
Okay, so thank you very much. It gives some insight.
So Vijay, we went over the hour. Do you still have time for two more questions?
Absolutely.
Okay, great. So then we hear from Kagan, if you're there, still online.
Hello, I think you hear me.
Yeah. Yes.
Thank you very much for this very interesting talk. I have two questions more on the application side. First of all, what do you think will be the near future, the emerging applications of these cooperative or collaborative tasks of the drones in near future? And the second question is also related with this. Do you think that the machine vision, especially the camera technologies, will take the lead, or the other technologies like infrared or time of flight, these kind of sensors will be the main perception part of this kind of cooperative tasks? What do you think?
Great question. Let me address the first one. So we work on a couple of different applications. So one is agriculture, where, again, at least in the US, you have these really large farms. Labor is tight, and you essentially want to do basically everything that I talked about. You want to cover large areas. You want to look for important information. You want to do this on demand. So the particular application we look at is tending to orchards. Can you monitor how fast trees are growing? Can you monitor how many fruit there are? Can you look for symptoms of disease? And you want to do this on an as-needed basis. And because you're looking at large areas, and because UAVs are limited in the amount of sensors they can carry, you might need multiple sensors. There's a lot of opportunity for coordinating or having lots of collaborating robots cover large areas to get this information. And I say this with some confidence because one of our labs startups, TreeSwift, has already raised funding for monitoring trees. So cutting down trees is something that we may wish to avoid if you're an environmentalist like me. But on the other hand, we need timber. So what they do is determine where the timber is and how it needs to be cut down. So essentially, they do get information about the inventory in forests, so they can inform timber management companies how to better harvest trees and how to better preserve the environment. So there's a real need for this. This is a huge industry. And it's really hard to do that with individual robots, and swarms, I think, play a big role. I think another spin-off company from our lab, which is Exyn Technologies, uses robots to mine for mining applications. Again, kinds of applications where you don't want humans to be working in dangerous environments. And mines are long, complicated environments with very little communications, no lighting, and you want to cover large areas. And you want to do this again on an as-needed basis. So that's another area where I think swarms are maturing. The area I think where I think there's a lot of potential is really underwater. It's not an area I work in. We are in a landlocked area in Philadelphia. We're not close to the ocean, but it is an area that I think has a lot of long-term potential in terms of applications of swarms.
Great. So let's then maybe take one last question, and then we let you go, Vijay, because I know you're very busy. So Ivan, you had a question about Linux?
Yes, thanks a lot, first and foremost, for a great lecture. Thanks, Vijay. I have a question coming from a biophysics background, where this interplay between entropy and energy and communication is very important. Do you think it will become of large importance, the cost of the communication, the energy cost of communication of these robots, probably what's linked with what Dario was talking about? Can that be a reason why the whole swarm is sort of slowing down? And also, I think Auke was also talking about that a bit, in terms of the hydrodynamic flow and everything. So do you think the communication between robots will scale the energy exponentially, or what do you expect it to be?
So if you look at drones, and if you look at the power budget of a drone, the processing and communication is just a tiny piece of that budget. So the communications challenges we have may well be because we're using off-the-shelf radios, 2.4 gigahertz, 5 gigahertz, Zigbee radios, and so on. But if you really wanted to engineer a swarm in a mission critical, safety critical application, which is important, if there are economic drivers, I think we could figure out how to engineer radios that could reach across large distances. But that's not how nature does it. So I don't think we should try to do it that way. I mean, and there's no compelling reason to do that. I think that's so it's not energy, but it's the fact that communications is inherently a noisy phenomenon, as is sensing. But the question is, what error rates are you willing to tolerate? And then how do you incorporate those error rates in your model of how you take actions? I'll give you another simple example for sensing. So detecting objects, tracking objects is a noisy process. So even the best detection algorithms maybe get to 90–95% accuracy. But then when you try to do pose estimation, there are errors associated with that. If you use learning, those errors are hard to characterize. And we still don't know how to derive control loops, feedback loops, that incorporate those error models into your feedback loops. Although there are many people that are trying to work on this problem. So to me, the fact that you have noisy sensors and noisy communication channels doesn't mean we should try to re-engineer the sensors, re-engineer the communication channels. We should figure out how to live with those noisy channels, noisy sources of information. And no, I don't believe power is the key limitation.
Thanks a lot. Thank you.
So wonderful. Yeah, I think we should let you go. So let's do an enormous round of applause. And I want to say Vijay has also beautiful TED Talks that I really recommend you to watch. So if you want to see more, please watch the TED Talks. And Vijay, thanks again so much for a really wonderful talk.
Hey, thank you once again for inviting me. Really, really a great opportunity. But I look forward to doing this sometime in person. Lausanne is a beautiful city, and it's been a while since I visited. Last time was Alcario had invited me, and I'll thank you for inviting me to do this virtually.
Yeah, no, absolutely. We owe you a nice dinner, a nice bottle of wine. So we have double dinner next time you come here.
Absolutely, absolutely.
So thanks everyone for watching. It was great. And I don't know if Jan, you want to conclude for the next talks, or a little conclusion on your side, Jan?
I can only second you. Thank you so much, Vijay, for your talk today. We will announce the next talks via the social media newsletter, so please feel free to subscribe and follow us, and hope to see you soon. Bye, stay safe.
Great. Yeah, bye-bye. Bye-bye, everyone. Thanks again, Vijay. Wonderful.